Welcome to This Explainer. I am absolutely thrilled you're here today because we are going to unpack something that honestly feels like absolute magic, but is actually a masterpiece of modern engineering. We're talking about speech processing. Today, we're going to map out the entire journey of a spoken word. We'll trace it from the moment it's just a spark of thought in your brain as it travels through the air as sound waves, all the way to how it's ultimately decoded and understood by artificial intelligence. Let's get started.
Okay, let's dive into this. We talk to our phones, our smart speakers, our cars on a daily basis. We ask for the weather, we set our kitchen timers, we literally dictate entire text messages on the go. And they just kind of get it. But to understand how these machines decode our voices, we actually have to take a step back. We need to look at the messy, complex, and totally fascinating reality of human speech itself. Because before a machine can process a word, a human actually has to speak it.
Section 1. The anatomy of sound, where human speech begins.
To teach a computer to hear, we first have to understand the basic building blocks of language, the ones we use every single day, mostly without even realizing it. It all starts right in your head with something called a phoneme. A phoneme is basically the smallest unit of sound that distinguishes meaning in any given language. But here is the critical part. It is entirely a mental representation. It's what you intend to say, not the physical sound. For instance, think of the word puff. In your brain, that's stored as 3 distinct phonemes: the puh sound, the sound, and the fuh sound. If we were to swap that F out for a K, we get a totally different word, puck. That simple swap completely changes the meaning, which is exactly how we know F and K are distinct phonemes. It's essentially the mental blueprint of the word.
Now, what's really interesting about this slide is the difference between what we think we're saying and what actually physically comes out of our mouths. Over on the left, we've got the phoneme, that mental blueprint we just talked about. Linguists write this out in what's called broad transcription using slashes. But on the right, we have the phone. The phone is the actual physical sound produced by our vocal tract, and that's written in narrow transcription using brackets. So when you actually say puff, you don't just say a sterile, clean puff. You actually release this tiny puff of air. In linguistics, that's called aspiration, and it's represented by that little superscript H you see there. You intend the phoneme, but you actually produce the phone.
Let's look at how this plays out with real-world accents. Take the word water. Now, if you're an American English speaker, your brain's mental representation, the phoneme, definitely contains a hard T. But when you naturally speak the word in conversation, you don't really say water. You say something more like water, using this really quick sound called a flap, which is written like that little hook symbol on the slide. Now, because pronouncing it as a flap doesn't suddenly change the meaning of the word in English, we call these variations allophones. Allophones are really just different ways to physically pronounce the exact same mental phoneme depending on the environment of the word. Pretty cool, right?
Section 2. Turning audio into data, how machines see sound.
Okay, so we've gone from the brain to the mouth. And now, that messy physical sound wave is floating out in the air. How on earth does a computer, a machine that literally only understands ones and zeros, make any sense of it? Well, it uses a very specific pipeline to digest audio. First up is signal segmentation. That continuous, messy sound wave is chopped up into tiny, manageable chunks, usually just 20 to 30 milliseconds long. Second is feature extraction. Here, the raw audio is transformed into a much richer format, like a spectrogram, to really highlight the important acoustic features. Third, we have token embeddings. Those features are converted into numerical vectors. You can think of these as math equations that represent the sound. And finally, sequence processing. Those numbers are fed straight into a complex neural network, like a transformer, which then looks for patterns over time.
Now, step 2 of that pipeline relies heavily on spectrograms, which are basically the machine's visual ears. A spectrogram takes a sound wave and plots its frequency against time, using color to show the amplitude or how loud it is. So the brighter or darker regions on the plot represent more acoustic energy. The absolute darkest regions show us what we call formants, and these are the distinct peaks in the frequency spectrum. By looking at these visual patterns, AI models, like hidden Markov models, can literally see the properties of human speech and identify exactly which physical phoneme was just spoken.
Section 3. The wake word challenge. Always listening, rarely draining.
So, we know how machines understand speech, but there's a massive hardware catch. Your smart speaker is always listening for its name, right? But if it ran a massive, complex neural network 24/7, its battery would die in minutes, or your electric bill would go completely through the roof. To solve this, engineers use a brilliant 2-pass system, and this slide brilliantly illustrates it. Think of it like a nightclub.
Level 1 is the always-on processor. It uses very low power, runs a simple deep neural network, and basically acts as the bouncer. Its sole job is to be highly sensitive. If it hears anything remotely sounding like the wake word, it wakes up Level 2. Now, Level 2 is the main processor, the boss. It consumes high power and runs a massive complex model. The boss is tuned for high precision. It's there to double-check the bouncer's work. If it really was the wake word, the system fully activates. If not, the boss goes right back to sleep, saving your precious battery life.
Section 4. Measuring AI performance, grading the machine.
So how do engineers actually know if their bouncer and boss are doing a good job? We need concrete ways to measure them. To really wrap our heads around these evaluation metrics, I want you to imagine you have a robot, and its sole purpose in life is sorting apples from a basket. It needs to pick out all the perfectly good apples and leave the rotten ones behind. How do we grade this robot? We can't just vaguely ask, is it accurate? We have to ask two very specific questions. How exact was it, and how complete was it?
This brings us to two absolutely crucial concepts, precision and recall. Precision is all about exactness. Out of all the apples the robot actually picked out, how many were truly good? If it grabs a rotten apple, precision drops. In our devices, high precision stops false positives. It's what stops your speaker from waking up when you didn't even call it. Recall, on the flip side, is about completeness. Out of all the good apples sitting in that basket, how many did it manage to successfully find? If it leaves a good apple behind, recall drops. High recall stops false negatives. It ensures your device doesn't flat out ignore you when you're actually talking to it. It's a lot like a brain surgeon removing a tumor. They've got to get all the bad cells, which is recall, without removing any of the good cells, which is precision. It's a constant, tricky trade-off.
To manage this trade-off, engineers building keyword spotting systems use something called a DET curve, or detection error trade-off curve. While you might have heard of ROC curves before, DET curves are really the ultimate tool here. They plot the false negative rate against the false positive rate on a normal deviate scale. What this means visually is that they create this beautiful, linear, and symmetrical line that makes the trade-offs blindingly obvious. Developers can look right at a DET curve and exactly tune the threshold to perfectly balance saving battery life against making sure the device always answers when you call its name.
Section 5. The state of the art. Where are we now?
To wrap up our journey, let's look at what all this linguistics, spectrogram processing, and precision tuning has culminated in today. So the crucial point is that we have moved way, way beyond basic phone recognition. We are now officially in the era of open source speech giants. Take Distill Whisper, for example. It's 5.8 times faster and about half the size of the original OpenAI Whisper model. Plus, it uses a really clever technique called pseudo-labeling to eliminate those weird AI hallucinations. Then there's Parakeet, built by NVIDIA and Suno. It's an XXL fast conformer transducer trained on a staggering 64,000 hours of speech, which makes it incredibly fast, like 10 times faster than Whisper. And finally, Canary 1B. This is a massive 1 billion parameter model that doesn't just transcribe speech. It dynamically translates it across English, German, French, and Spanish, complete with actual punctuation control. Which leaves us with this final thought. We started this journey with the human intent, that tiny, invisible phoneme inside your brain. And we ended up with a billion-parameter neural network transcribing multiple languages in real time. As these models become faster and honestly more accurate than human transcribers, we're rapidly approaching a horizon where machines don't just mechanically decode our audio, but truly understand our actual meaning. Thank you so much for joining me on this explainer today. I highly encourage you to go explore the source material and dive even deeper into this incredible world of speech processing. Keep learning, and I'll see you next time.